Ever wondered why planets don't fly straight out into the universe or crash into the sun? That's a question that has puzzled thinkers and scientists for centuries. It's a conundrum that takes us to the heart of our mysterious universe and the intriguing ballet of celestial bodies. Planetary motion, or the way planets move around the sun, is a fascinating dance of physics and mathematics. It's not as simple as tossing a ball and watching it arc through the air. There are unseen forces at work, forces that keep our planet Earth and its celestial siblings in their paths and prevent them from hurtling off into the cosmic void. One of these invisible forces is gravity, a fundamental principle that governs the universe. It's the glue that holds everything together, from the smallest particles to the largest galaxies. And it's gravity that keeps the planets in their orbits around the sun. But how exactly does gravity work in shaping these orbits? Why are some orbits perfect circles while others are more like stretched out ovals? Gravity pulls objects towards each other, and in the case of a planet and the sun, this force of attraction is balanced by the planet's desire to travel in a straight line. When you combine these two factors, the result is an elliptical or oval-shaped orbit. But there's more to it than just that. These orbits are not static or unchanging. They're dynamic, like the universe itself. They shift and change over time due to the gravitational pull of other celestial bodies and the ever-changing dynamics of the universe. Understanding these shifts and changes is crucial to understanding the universe and our place in it. Unraveling these mysteries of planetary motion is a task that has occupied some of the greatest minds in the history of science. It's a task that requires a deep understanding of the forces at work in the universe, a keen eye for observation, and a mind capable of making sense of complex mathematical relationships. This is where Johannes Kepler, a 17th century astronomer, comes into play. Johannes Kepler, ever heard of him? Well, he's a big deal in the world of astronomy. Born in the late 16th century in Germany, Kepler was an astronomer, mathematician, and astrologer. But he's best known for his eponymous laws of planetary motion, three principles that forever changed our understanding of the cosmos. The first law shattered the age-old belief of circular orbits, introducing the concept of elliptical planetary paths. The second law, also known as the law of equal areas, redefined the speed at which planets move in their orbits. The third law, the harmonic law, established a relationship between the time a planet takes to orbit the sun and the size of its orbit. Kepler's revolutionary ideas laid the groundwork for Newton's law of universal gravitation and effectively marked the dawn of modern astronomy. So, now you know, Johannes Kepler is not just a name in a textbook, he's the reason we comprehend the universe the way we do. Now, let's dive into Kepler's second law, also known as the law of equal areas. Imagine you're tethered to the sun by an invisible line. A peculiar thought, isn't it? But this is essentially the working principle behind Kepler's second law of planetary motion. This law, also known as the law of equal areas, can be visualized as an invisible leash between a planet and the sun. Let's break this down. Imagine a planet revolving around the sun. Now let's pretend that there's an invisible leash connecting the two. As the planet orbits the sun, this invisible leash sweeps out a certain area. According to Kepler's second law, this leash will sweep out equal areas in equal amounts of time. Now, this might seem abstract, so let's paint a clearer picture. Picture yourself spinning around, holding a long piece of string with a ball at the end. When the ball is close to you, it moves quickly, and as it swings out farther, it slows down. In the same way, a planet moves faster when it's closer to the sun, and slower when it's further away. Now, you might be wondering, why does this happen? Well, it's all because of the sun's gravitational pull. When a planet is close to the sun's gravitational pull is stronger, causing the planet to move faster. As the planet moves away from the sun, the gravitational pull weakens, and the planet slows down. So, the invisible leash between the sun and the planet isn't just a fancy metaphor. It's a way to visualize the sun's gravitational pull and how it influences the speed of a planet's orbit. It's this balance between distance and speed that ensures the leash sweeps out equal areas in equal times, regardless of whether the planet is close to or far from the sun. This is the essence of Kepler's second law of planetary motion. It's a fundamental principle that has shaped our understanding of how planets move in their orbits. And it's all based on the idea of an invisible leash and the constant dance between distance and speed. So, in simple terms, planets move faster when they are closer to the sun, and slower when they are further away. So why should we care about Kepler's second law? Well, let's dive in and find out. This law, seemingly simple and mathematical, has profound implications and practical applications in our everyday lives and beyond. Imagine you're planning a trip. You'd need to know your destination, the distance, and the time it will take to get there, right? The same goes for space travel. Kepler's second law assists scientists in predicting the positions of planets at any given time. This understanding is critical to planning missions to Mars, Jupiter, or even the outer edges of our solar system. This law isn't just about far-off space missions, though. It's closer to home than you might think. Every time you use GPS to find your way to a new restaurant or when you check the weather forecast for your weekend plans, you're indirectly benefiting from Kepler's second law. How so? Well, these services rely on satellites, and these satellites are deployed and function based on the principles of this very law. So, you see, Kepler's second law is woven into the fabric of our modern world. It's the invisible hand guiding the satellites that connect us, inform us, and help us explore our universe. But it's not just about practicality. Kepler's second law also contributes to our understanding of the cosmos. It helps us grasp why planets move the way they do and why their speeds vary. It's a foundational piece of the cosmic puzzle, helping us decode the mysteries of the universe. In essence, Kepler's second law is a testament to the beauty of scientific discovery. It's a centuries-old law that continues to be relevant, demonstrating how the pursuit of knowledge can have lasting, tangible impacts. So the next time you look up at the night sky, remember this. Each twinkling star, each planet, each satellite passing by is moving according to the principles laid down by Johannes Kepler over 400 years ago. Kepler's second law, though centuries old, still plays a crucial role in our exploration and understanding of the vast universe.